Okay, hello everyone and welcome back to your YouTube channel. And welcome to this amazing video today. And today we are doing something quite interesting. As you must be aware, I am recording this series of videos because we are working with power system dynamics. And in particular, this series of videos is related to time domain modeling and simulation. And you must remember that in the previous video I was working with a very specific test system. The first video was introducing the test system. The test system is basically a synchronous machine that is connected through a transmission system to an infinity bus bar, okay? And one video later, I start to calculate and set all the pre-contingency analysis. Okay, I mean the second video was related with preparing PowerFactory and using PowerFactory to calculate the pre-contingency steady-state conditions. Now today I have another very interesting video. Today we are working with initial conditions, okay? In this video I will keep using the same test system, the single synchronous generator connected to an infinity bus bar using a transmission system. This is a very simple, very basic power system, but the idea is that I will discuss the fundamentals related to initial conditions, and then we will use DIgSILENT PowerFactory to calculate the initial conditions, okay? Don't be confused. Initial conditions is very different to a classical load flow, okay? And that is especially true if you are working with DIgSILENT PowerFactory, okay? There is a module inside PowerFactory for calculating the load flow. That is the steady-state condition, okay? And then when you are working with the time domain simulation, there is a specific calculation function that is dedicated for calculating the initial conditions, okay? Well, today we are working with the same approach. We are taking the same test system. You must remember this is the test system that we have been using for a couple videos. This is a synchronous generator. Synchronous generator is connected to a bus bar. This is a 11 kV bus bar. Then there is a step-up transformer. The step-up transformer is going up to 232 kV. That is the high voltage bus bar. And then two transmission lines, they are delivering the power to the infinity bus bar. And here we have this equivalent of a huge power system, okay? I remember we create this model inside PowerFactory. Also, you can go to my GitHub repository. You can download from there, okay? But also, I remember that the second video we set up the steady-state calculation in order to obtain this famous power factor 0.8 at the bus bar. And I remember that we use over there the station controller. That is a very interesting feature inside PowerFactory to do the job, okay? And what is the job today? Well, today we have a very interesting day because you must remember from the classes, okay, from the theory. Always I try to connect the theory with the reality, okay? The theory is what allows people to understand and to explain properly the situations, okay? You must remember that I say to you that any single dynamic system can be represented but by a set of differential algebraic equations, and that is what we call the DIA model, okay? The differential and algebraic equation model is basically this. This is a vector form, okay? This is the vector representing the derivative of the state variables. Here we have a vector representing the output variables, and here we have two functions where we have the the connection between the state variables, time, and also the uncontrollable parameters, okay? You must remember we discussed this, we use several approximations and so on, but at the end, that model can be applied for electrical power system. What I'm trying to say is, if you are working with power system dynamics, you must understand the differential algebraic model, and also you must understand this model that is presented here on the right-hand side. And that is the basic way to represent a classical power system, okay? You have here some Thevenin models at this terminal representing the generators, and on the right-hand side you have also some current sources representing some elements. They can be loads, they can be power electronic converters, they can be anything like that. And then we use for the classical time domain analysis, Tracian analysis, for electromechanical purposes, we use a set of algebraic equations describing the network model, okay? If you want to learn more about that, go to my YouTube channel. There are a specific video, probably two hours, doing the explanation, okay? But what you need to understand is that the basic point is we need to define the differential algebraic equation model, and then we need to solve the model, okay? And that is what we need to do. Any software is doing what I explained before. Internally, any power system analysis software, inside the software, there are the equations. The equations are created with the parameters that you input in the model, and then the model is solved, okay? The classical approach used for almost every single power system analysis software is what we call the partition explicit, okay? What is the partition explicit? The partition explicit is the approach that is quite well applied for power system analysis. It's basically solving the differential equations and the algebraic equations in a separate way, okay? What you are doing is solving first differential equation, then with the solution of the differential equation you go and solve the algebraic equations, and you keep doing this until you reach the whole simulation time, okay? What I'm trying to say is that partition explicit method is basically this solution of the differential algebraic equations, where you use explicit numerical integration to solve the differential equations, and then you use any algorithms to solve the nonlinear algebraic equations, okay? Typically, every single power system analysis software, they have very strong routines for explicit numerical integration, okay, like Runge-Kutta, predictor correctors, and so on. Many of the commercial software available in the market, the full details of the explicit numerical integration is industrial secret, and it's something similar to the implementation for the case of the algebraic solutions, okay? In general terms, basically what we are doing for the network, for the algebraic equation, is using any numerical methods like Newton-Raphson or something like that, okay? Here we have here the flow chart, and the flow chart is typically showing you the process that we use to solving the differential algebraic equation model using the partition explicit, okay? We start let's say we start the process, then we read the data, then we create the initialization or the calculation of the state variable, okay? This is the point where we are today. We are calculating today the initialization of the state variables, and that is the job in this video, okay? In the next videos, I will discuss this series of steps. However, those steps are done internally by the simulation software. For instance, DIgSILENT PowerFactory, they do everything here. Everything here is done internally, okay? In fact, also initial conditions are calculated internally, okay? But I will use the software in order to demonstrate you that you are learning something in this course, that you are learning about initial conditions in the test system that we have been discussing, okay? Let me keep in a practical way, okay? We have been working with this test system. This test system is extremely simple: generator, transformer, two transmission lines going to the infinity bus bar, okay? We already run the load flow in this test system. We calculate the voltages, we calculate the active and reactive power flow. We know the power factor at the infinity bus bar. We calculate the power flow, okay? And from there, we know the steady state behavior of this system, okay? For instance, we remember that in the previous video we discussed about this current. In per unit, this current is 0.75 per unit at minus 36.86, okay? However, in that discussion, I use this reactance diagram. Okay, this is the reactance diagram. In this reactance diagram, the transformer, the lines, and the generators, they has been converted into a model, and now we have a circuit that we can use for calculations. Okay, but if we go into the classical transient analysis, when we are interested on calculating the initial conditions, well, what we are doing is calculating, for instance, several variables that they are extremely useful for the transient. Okay, for instance, one of the very important variables that we need to know is what is the internal voltage of the synchronous generator. If you look over here on the bottom left-hand side, you can see that there is a letter E, and that is representing the internal voltage of this very specific synchronous generator. Remember, here we are using the classic the analysis of the classic stability problem. Okay, for that reason we are using the most simple model for the generator. In this case, we are using the voltage behind the reactance, and that is the simplest model that you can find. Okay, if you are using the 7-order model or any model like so complex like the one used typically inside PowerFactory, of course you will have more state variables that you need to know. Okay. Well, the job now is to calculate this internal voltage. And the reason that we need to know this internal voltage is because inside that internal voltage, we have one of the state variables. If you remember the most basic equation that we used to describe the dynamic of the electrical power system considering synchronous generator, the most basic model is the swing equation. And the swing equation is a second-order differential equation in terms of delta, the rotor angle, okay? Well, let me tell you the following. When we are using this simplified model, to be honest, we are using a model where the internal voltage, the angle of the internal voltage represents that rotor angle, okay? But before going so deep over there, my job right now is to calculate that internal voltage, okay? And that internal voltage is extremely simple to calculate. All my students, they are extremely expert on circuit analysis, okay? And we used this circuit before. We know the current. The current is 0.75 per unit at minus 36.86. That is the value for the current. But if you look this circuit is extremely simple. We have here a voltage source, we have here a series of different reactants, and then we reach here this voltage, okay? Now, what we can do is use just basic circuit analysis, and there is something called Kirchhoff voltage law. Kirchhoff voltage law is probably the best tool that allows you to calculate the that internal voltage. For instance, we can use here, we can move inside this closed loop and write the Kirchhoff voltage law. For instance, this internal voltage should be equal to the voltage drop across this series of reactants, And we can create an equivalent for this series of reactants, okay? And then we can go back through this ideal voltage and close the loop. And that is this equation over here, okay? What I'm telling you is that this equation over here is representing the equation defining the voltage across this loop, okay? We have the internal voltage of the machine, that this is what we are looking for. We have here the series of components. We have several components, and then we have here the voltage across the infinity bus bar, okay? The only thing that we don't know is in that equation, in that Kirchhoff equation, the only thing that we don't know is the value of these reactants over here. And to be honest, that is the reactance between those terminals over here. And you can see that there is a 0.2 in series with 0.2, and then we have this parallel but is in series with the other components. What I'm telling you is that you can find an equivalent reactance between the internal voltage of the generator, that is where the power is produced, and the infinity bus bar, that is the place where we want to receive the power, okay? And that is what we will do. Here you can see the equation. We can say that the reactance that is connecting the generator and the infinity bus bar is equal to the transient reactance, the axis of the generator, plus the reactance of this transformer, plus the parallel between those two transmission lines, okay? The good news is that two transmission lines, they have the same value, 0.15, and we can put together 0.2, 0.2, and 0.15 divided by 2. Finally, we get this beautiful value over there, and that beautiful value is representing here. You can see this is representing the reactance, the equivalent reactance between those 2 points over here, between this and this, okay? That is the reactance. And that reactance is going here into the Kirchhoff voltage law, okay? That is what I am trying to explain to you. Okay, now what we need to do is just substitute this value into the Kirchhoff voltage law equation, and that is here. And we know already the current, 0.75 minus 36.86, and we know the voltage of the infinity bus bar. Voila, we got a solution over here. What is the solution? You can see over there that the internal voltage is 1.246 per unit at 13.12, okay? That is basically the internal voltage of the synchronous machine, okay? Using this ideal model, using this basic ideal model, okay? What we need to do now is, okay, we assume, if you remember, we assume that this voltage is the reference, okay? Remember that we assume that the voltage of the infinity bus bar is the reference, and that is a typical case, okay? Because typically we assume that infinity bus bar is so large that the angle can be the reference and it's not moving, there is no changes on frequency, there is no changing on position. That is the infinity bus bar concept, okay? However, be careful at the exam, okay? Because in the exam, this angle could be different, okay? And if this angle, for instance, is 5 degrees, I mean, it's different to 0, okay, you need to make a compensation when you are calculating the internal voltage. And I will explain that. Give me a second, okay? If you look here, let me clear the screen. If you look in this phasor diagram, you have here the phasor diagram, and you can see the location for the internal voltage. This is 1.24 at 13 degrees, okay? And this is the infinity bus bar position, okay? 1 at 0 degree. The angle that is defined between the two phasors is the initial operating angle, that is the initial rotor angle, okay? In this very specific case, the numerical value is 13.21, okay? That is the value for the internal or initial operating angle, okay? But however, I say to my students, be careful, because in the exam paper, you can find that this angle over here, the angle of the infinity bus bar, is not 0. Imagine that this angle is not 0. Imagine that this angle is 5 degrees. Well, what will happen is that this phasor diagram will be rotated by 5 degrees, okay? And now this angle is impossible. This angle will be 18.2163, okay? Because the reference will be 0. This will be the reference. The reference will be 0 degree here. And then we have this voltage that is this is the infinity bus bar, and that is 1 at 5 degree. And then we have here the location for the phasor internal voltage of the synchronous machine, and this one is 18.21. The difference here is what we call delta 0. The angle between those two phasors is what we call the initial operating angle, okay? What I trying to tell you is you can have here the reference 0 degree, okay? For any problem, the reference is 0. We have here the voltage of the infinity bus bar, okay? And we have here the internal voltage, let's say, of the synchronous machine. The angle that is defining the rotor angle is this one, okay? This is the initial operating angle. This is the initial rotor angle, okay? Okay, now I explained this. Let me clear my whiteboard here, or blackboard. I don't know which name do you prefer. But here, the thing that we need to remember is this angle here, okay? This angle is 1313.21, okay? Because that is the internal angle. That is the internal angle of the synchronous machine, okay? Now let's do the following. Let's go to PowerFactory, and we need to demonstrate that this is the proper angle inside PowerFactory. And also, let's try to find this internal voltage, okay? And I will explain that, okay, in a minute. Let's do the following. Let's go to PowerFactory, okay? Let's go to PowerFactory, and there we can do the job, okay? Okay, right now we are here inside the DIgSILENT PowerFactory. And as you can see, we have here the system that we have been using for a while, and that is the single machine connected to the infinity bus bar using this step-up transformer and two transmission lines. Okay, we are familiar with this. Let me run the load flow. Okay, the load flow is defining the state performance, and you must remember we obtained those values before. Okay, this is the power factor here that we have been fighting to get, and this is the power factor that we have in the infinity bus bar. And on the left hand side you can see that we have the full details about currents, active power, reactive power, and so on. Okay, but the important thing here for you is that you must be aware that we are working in steady state conditions. Okay, if we want initial conditions, then, well, we need to start to work with a new calculation function inside PowerFactory, okay? And that calculation function is here. You can see that PowerFactory has a very important module that is the simulation RMS and AMT, okay? That is the calculation function that we will be using for time domain simulations, okay? And that is a very important point. However, before we start to do that, let me select here, and you will identify here at the top. You can see here at the toolbar, you can see you can see the icons that we need to use for time domain simulations, okay? Okay, but let me keep going here. The first step before we run any calculation regarding initial conditions, the first step is that we need to prepare. We need to set up the system, okay? And there are very important things here that you need to be aware, okay? I believe that all my students must understand the following. When we are working with load flow, everything is simple, okay? Power flow is for kids. I know that a lot of people will say, okay, it's not for kids. Well, typically it's for kids, okay? Even a kid can run a load flow. But for power system dynamics, the situation is a bit more complex, okay? Especially because you need to be familiar. You need to be familiar and understand the models, okay? And here in this system, the most important device that is producing power system dynamics is the synchronous generator, okay? For that reason, I open here. You can see we have the synchronous machine. This is the element synchronous machine. This is the object that is representing the synchronous machine here inside the network data. But all my students, they are clear that the model that we use for the dynamics is defined inside the type, okay? Let me click here. And now in front of you, you have a window. And that window is representing the type synchronous machine. And because we are starting to do something serious, let's go here to RMS, okay? Let's go here to RMS. Right now, in front of you, you have one of the most important aspect of using the synchronous machine inside PowerFactory, okay? The first thing that you must notice is I am here inside the simulation RMS, and at the top, there are something that is called the model, okay? PowerFactory has been working extremely hard with the model of the synchronous machine, and since several years, they have been including more and more features and more characteristics about the dynamic model of the synchronous machine. If you prefer to use the standard model, you must be aware, okay? You must be aware. This model is a full representation of all the regimes that you can simulate for the synchronous machine. That is the reason that the model is asking for subtransient, transient, and rotor and stator reactance and resistance, okay? This model is the most detailed that you can have inside PowerFactory, okay? Sometimes I saw people using this model to try to replicate results of the equal area criteria or for analyzing classical transient stability. That is not fair, okay? That is not totally right, okay? Because PowerFactory has here a specific model that is called the classic model, okay? Of course, this model is included in the most recent versions. If you are using version 15.1, of course, you don't have this classical model, but the classical model is the one that we need to use if you are doing classic transient stability analysis. Because this model, if you press here, you can see how the model is totally simplified, okay? Because now you can see that less data is required. For instance, the data that we need to put here right now is only the transient D-axis reactance that it was provided at the presentation, okay? If you go back to the presentation, you must remember that at the very beginning, we say we provide data for this transient D-axis reactance, okay? And you must remember that transient D reactance is 0.2, and for that reason we keep here 0.2, okay? That is the idea. That is the idea, okay? Then we need to define the inertia constant, okay? And to define the inertia constant, if you go back to the presentation, let me go back here for a second to the presentation. It's not this slide. let's go back to the presentation here. Yes. If you go back to the presentation, you must remember that at the very beginning I told you, that the subtransient reactance is here, the transient reactance is here. It's 0.2 per unit, okay? And also we receive data about the inertia constant. In this case, the inertia constant is 8.45 megajoule per MVA, okay? That is the data that is given to us. That is the data represented the synchronous machine. Now what we need to do is basically go to PowerFactory, and here we need to put the stator reactance, okay? 0.2 is fine, but we need to define also the inertia, okay? You can see here, this is the inertia, and what we will use is basically here the inertia constant, and we will use 8.45, okay? From there, well, we are done. Now we have here the data. We include the data of the inertia constant, and we include the data of the D-axis reactance, okay? Now it's time to run the initial conditions, okay? If you are following my videos and you are in my classes, of course, you already got a class explaining how to run initial conditions inside PowerFactory. It's extremely simple, okay? Here at the tool bus bar here, the toolbar over here, you can see that there is an icon, and that icon is related to calculate initial conditions, okay? If we press over there, you can see that there is a dialog in this window to define the initial condition calculation method, the simulation method, the network representation, and so on, okay? I run another video with the theory and all the explanation, but basically the simulation method is the way that we are solving the and the assumptions that we are making for the dynamic models, and in this case we are calculating the electromechanical transient considering RMS value, fundamental frequency for the network, okay? That is the reason that we are using here the RMS value, okay? And the network representation, I mean transmission system, transformers, and so on, we are using just the positive sequence representation, okay? For that reason, we need to keep here just the basic balance, positive sequence balance representation, okay? What this menu is telling you is that in this case, when we run initial conditions, PowerFactory will be solving the differential equations, but for the electromechanical transients, using RMS values, fundamental frequency, and only considering the positive sequence, okay? There are more configurations here about step size for the integration, solver equation, blah, 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 blah. I will not go in details over there because this is not a training. This is not a training about the DIgSILENT PowerFactory. This is just a basic explanation for my students in order that they can perform the basic initial conditions, okay? Now what I will do is the following. What I will do is press this button, execute initial conditions, okay? And suddenly anyone that is not familiar with PowerFactory, they will say, okay, what's happening here, okay? Okay, let me do it in slow motion, okay? Let me do it in a slow motion. I just amplify here, open a bit wider the output window. Let me clear the output window, okay? The first thing that I would like to show you is when you run load flow, we did this before. PowerFactory is telling you, okay, we have a reference, and that reference is the infinity bus bar, okay? We are using Newton-Raphson algorithms, and then after 3 iterations, okay, we have the convergency, and we solve the load flow, okay? That is what happened when you press here the command load flow button, okay? That is what happened. But let me clear the output window, okay? If you are not expert in PowerFactory, probably you can be confused, okay? But let me tell you the following. when you run here, initial conditions, look over here. I run initial conditions. And what's happened? Okay. What you can see over here is that PowerFactory is telling you, okay, we have a local reference, and that local reference, as you can see over there, is the infinity bus bar. The system frequency is 50 Hertz, no problem. And then PowerFactory tells you at t equal minus 100 milliseconds, the initial conditions were calculated, okay? And that is true. What is telling you here, PowerFactory, is that the PowerFactory internally calculate the initial conditions. But now the question is, how do I show to my students that we got the initial conditions, okay? Well, and it's extremely simple. What I will do here is, again, use my previous defined additional test bot results, okay? If you remember, in the previous video, I installed here these beautiful additional toolbots, okay? Okay? Okay. Now let's edit this additional test bot result, okay? Let's edit that thing. And what I will do is append a row, okay? And double click. That is what I am doing here, double click. And now PowerFactory is allowing me to define the variables that I want to show here at my resulted bots, okay? I don't know if you noticed, but when we were running LoadFlow, PowerFactory automatically point the results variables into the LoadFlow tab. But right now it's indicating, and you can see in black color over there, RMS, simulation RMS, because we want, and PowerFactory will allow us to get the internal values over there, okay? The values coming from the RMS simulation, okay? Okay, let's do the following. Let's go and select here, select here, signals, okay? And right now you can see that there are several signals, okay? There are several signals, and you can see here that there are several signals, and there is a column indicating type. And for instance, you can see that there are excitation voltage, there is turbine power, for instance, but also we have here electrical power, that is an output. We have electrical frequency, that is another output. Terminal voltage, that is another output. But here, for instance, we can see the speed, okay? We can see the speed. This is an state of this machine, okay? We can see here phi is the rotor position of the d-axis, refers to the boost voltage, okay? And also, okay, let's select those one, okay? Let's select those one. I almost forgot. Let me include, as we did before, click here in order to show the name of the variable. We want to show the equal symbol, and we want to show the units, okay? I mean, it's a good idea to show the students that we are presenting the full results here, okay? And the units, okay? Done, okay? Now, as you can see, something very, very interesting here. Something very, very interesting here. Something that is worth to see is, okay, now we have, for instance, the internal voltage. The internal voltage here is VE, okay? Is the variable named VE. And VE is representing the internal voltage of this machine, okay? If you remember, let's go back here to my calculations. Let me go back to the presentation for a second. When we run the calculations, look over here. Internal voltage equal 1.247 per unit, okay? This is, again, the internal voltage. Remember that internal voltage is, let me use the laser pointer here. We are here at, this is the internal voltage of this synchronous machine, okay? And you can see the numerical value. The numerical value is 1.2467, okay? Now let's go back to PowerFactory. If we go to PowerFactory, voila! The internal voltage here that is presented is 1.247, okay? I will say that is an amazing match, okay? That is an amazing match. We can see over there that this very specific value is matching the voltage, the internal voltage that we were discussing before, okay? Now what we want to see is the angle of that internal voltage, okay? And to do so, let me do again, let me open here, edit this additional test result. Let me append an arrow, insert append a row here, yeah? And now let me find, okay, I would like to, let me go to calculations here, calculations, okay? And let me find, where is feed rod, okay? Feed rod is here, yes. And now look over here. If you look the variable feed rod, the feed rod is representing 13.214 degrees, okay? That is the angle that we obtain here in PowerFactory. And let's compare that angle with the angle that we got in the manual calculation, okay? If we go here to the manual calculation, look over here, 13.216. And inside PowerFactory, we get 13.214, okay? That is similar, okay? What I show you, what I did right now is to demonstrate that when we run initial conditions, we are calculating more variables that the variables that we calculate using load flow. The initial condition is much more than a classical or basic load flow, okay? When we are running the initial conditions, we take the differential equations, okay? But we assume that the system is in a steady state. That means that the differential component of all those differential equations is equal to 0. There is no variation on the state variables, and from there we obtain a set of algebraic equations, and from there we can calculate the value of the states variable using the steady state assumption, okay? That is what the initial condition button do when we are using the these initial conditions, okay? Something that is quite interesting, I will show you here. Let me calculate here the load flow. If we calculate the load flow, look over here. There is not angle, there is not internal voltage, there is not, because again, when we use this button over here, and this is the COM INC, this is the COM initial conditions, when we use that, we are calculating more. We are calculating the internal voltage, we are calculating the angles, we are calculating speed, okay? Of course, the initial rotational speed here is 1 per unit because this is a synchronous machine. And synchronous machines are working at synchronous speed in a steady state. That is the reason that we got over there 1.0 per unit, okay? Probably the last question before I close this video and finish this video is the classical question from my students, okay? How do you know that the variable feed rod is the variable that you were looking for, okay? That is a typical question. How do you know that is feed rod? Because I want my student thinking, okay? I don't want a student that then they will go to the company and they will use feed rod, and then somebody asks you, why you are using feed rod? No, because the professor used feed rod. No, that is unacceptable, okay? That is unacceptable. you need to think about, be sure about what you are doing, because there are many angles, that they can be calculated inside the DIgSILENT PowerFactory, and every single of those angles has an application, okay? For that reason, what you need to do is you go here to the user manual, and there is technical reference for the models, okay? Technical reference for the models, okay? A PDF file will open, okay? This is the PDF file, and what I will do, you must be familiar with this document. This is the PDF file of the technical reference overview, and you will go to the Synchronous machine. Let me find here Synchronous machine, and you will open the technical reference, okay? Technical reference from PowerFactory is extremely well done, okay? That reference has been improved for many years, and it's including a lot of information today, okay? I need that all my students go here and check at the RMS simulation, okay? Section number 6 of the technical reference of the synchronous machine, section number 6. You can see this is the DQ axis model, okay? And here you have the different input parameters that you can use, okay? And here the calculation for the different time constants, subtraction constant, the axis, open circuit or not. And here is how you can convert from short circuit to equivalent circuit parameters, okay? You must remember that you took a class about electrical machines, okay? And then we have here, this is the standard model that we were discussing about. By default, PowerFactory use the default mode. And the default mode is quite interesting. There are some algebraic equations, there are some differential equations, okay? When you are using the standard model, the first thing that you need to understand is that the flux leakage is used as a state variable, okay? That is the most serious representation that you can do for the synchronous machine. Of course, the Q axis, okay? And then if you keep going here, this is the equation, then we have the equation for the RMS model, and keep going, this is the incremental components, RMS component, and this is the AMT model, and okay, here we have the mechanical equations, okay? This equation over here is the mechanical equation used by PowerFactory to solve the dynamic, okay? Here, as you can see, this is the speed derivative. This is the equation 95 is the similar equation to the swing equation, okay? The swing equation, remember I showed you, is the second derivative of the rotor angle, but that is equivalent to the first derivative of the rotor speed, okay? PowerFactory internally is using the first derivative of this rotor speed. And also you must remember that at the very beginning I showed you the swing equation using torques, okay? Mechanical torque and electrical torque, okay? PowerFactory use a full version of this equation. This is mechanical torque, this is electrical torque, but PowerFactory is also able to include damping torque and damping torque inside the machine, okay? This equation 95 is the equivalent to the swing equation or the electromechanical model used by the DIgSILENT PowerFactory internally, okay? And here you can see the representation, you can see the equation 97, and that is to represent the mechanical torque, okay? Here you have the damping torque, and you can keep reading, okay? What is the understanding of the acceleration time constant? PowerFactory spent over there some explanation and equations. That is extremely good for them that they provide this, okay? And this is the place that I was looking for, okay? This is the place that I was looking for. My students, clever students, they will ask me why you use feed rod, okay? Feed rod is here. You can see feed rod is here. Let me use this color here. No, I cannot use the color. Why not? Something is happening, but okay. Here is feed rod. You can see with my cursor, this is feed rod. This is the Q axis of the generator, okay? And this is the reference machine voltage terminal voltage, okay? What I'm trying to tell you is inside PowerFactory, there are many angles. There is feed rod, feed pole, feed rail, feed U, feed. And if you want to understand this, don't ask your professor. Come here and understand this, okay? Come here and read about feed rod, the external rotor angle of the machine, referred to the voltage of the reference voltage of the network, okay? Please, I highly suggest come here and read the technical documentation, okay? Right now, we have completed the calculation of the initial conditions. We demonstrate that the internal voltage in this case is the value that we predict, okay? Here I have the circuit. You must remember, internal voltage 1.246. You can see here internal voltage 1.247, just a small difference. And the internal angle is 13.21, and you can see here feed rod, the internal angle is 13.214, okay? This video has been a short introduction, well, it's almost an hour, but this is the a short introduction about initial conditions, okay? Believe it or not, this has been 1 hour, but 1 hour is just an introduction about how to calculate initial conditions. My master students, the good news is they have something called independent studies, okay? Independent studies is the studies that they develop by themselves. They sit down, they are highly reflective. They think about what they are doing and how to do it and how to improve it and so on. They are extremely clever. They must spend this time, they must enjoy this independent learning. And one suggestion for all of them that they are very, very clever, go to the technical reference and read the technical reference, okay? I highly suggest that one of the products that you will do in your independent studies is read so much and understand so much about the technical reference inside PowerFactory, okay? Well, this is all about the initial condition calculation using DIgSILENT PowerFactory. I hope all my students enjoy this video. I hope all of them have the opportunity to learn something about this. Also, all my people in YouTube channel, I hope you enjoy this video. If you do it, please remember to use the like and also subscribe to the channel, okay? In order that you can receive notifications about the updates and so on. Thank you very much for watching this video. I will see you very soon in the next one. Thank you. Bye.